The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Let's go back to our discussion of spectral broadening. And what I started to derive for you is perturbation theory of spectral broadening, which is a very general framework. I like it because it really provides new insight into spectral broadening, but I also hope it provides new insight for you what time-dependent perturbation theory really is. So what we did in this lecture is we pretty much did standard time-dependent perturbation theory. We just did it by assuming that we have a general time-dependent perturbation. I'm not yet telling you what the time-dependent perturbation is. It has actually fluctuating, it has inhomogeneities, it has everything in it which will later lead to line broadening and line shifts. And the important quantity which is now describing everything we are interested is the correlation function between the perturbation at time t prime and t. And we call this correlation function G, and it is either the correlation function G of t or its Fourier transform, which tells us what the excitation rate of the system is. So I want to give you sort of two summaries now. And they're both general to perturbation theory, but I have to say, I myself learned something about time evolution of quantum systems from those examples. So what we get is the very generic thing that when we look at the probability to be in the final state, the amplitude v of t squared, we start out quadratic. A very general behavior of any quantum system, because you have an equation which linearly puts amplitude into the excited state and the probability is quadratic. And also, this is the beginning of a Rabi oscillation. And the Rabi oscillation starts out with zero slope. But then you have some decoherence time. The fields are no longer driving the system in a coherent way. And then that's where we enter the regime of Fermi's golden rule. The probability to be in the excited state only goes linear. And this is when we have rate equations. Let me sort of show how it comes about in equations, which I think is really nice. The differential equation says that in a time delta t, we add amplitude delta t to the excited state. And so the amplitude we build up is, I may have dropped an h bar here, or maybe I measure v in frequency units. It's just the matrix element times delta t, and we usually call the matrix element the Rabi frequency over 2a. So you should think about it that we add sort of this amplitude. And as long as we are coherent, I have to take the amplitude, 1/2 the Rabi frequency delta t and square it, and here you get the quadratic behavior. This behavior, you so have constructive interference. All those delta b's are added in a phase coherent way. But this behavior ends, of course, at the coherence time. So once, just get my notes. So when the time becomes comparable to the coherence time, we are adding amplitude not as constructive interference, we are adding b square in quadrature. It becomes sort of a random walk, and we add things in quadrature. So what happens is, at the coherence time, we have created an amplitude which is given by this expression. But now, if time goes by, we add in quadrature t over tc chunks of that. So therefore, our b square, which we build up with time, is linear in time and is omega rabi squared over 4, the matrix element, times the coherence time tc. And this here now is our rate in the rate equation. And this is also what we exactly got out of the correlation function formalism. So this is how you should think about it. You go from constructive interference in amplitude in adding things in quadrature. Let me maybe add one more discussion to it, which I hope will help you to see the big picture. We have a matrix element V. And if I just asked you, think about Fermi's golden rule, you would find out that the rate is V square times the density of states at the resonance. And sometimes, instead of the density of states, you write a delta function, which is just a placeholder that you should do an energy integral, and then you get the density of states. Okay, so this is sort of Fermi's golden rule, and it should be an old hat to you. But what I told you now is that what is involved here is the from the time integration is the correlation function v of 0, v of t at two different times. But then, because of the time integration of Schrödinger's equation, we had a time integral dt. But v of 0, v of t, remember, we have a correlation between the field v of 0 and then it decays with time. This here can be written v of 0 squared times the correlation time tau c. So therefore, the correlation function, it's a general formalism. It allows us to deal with all time dependencies, but in essence, the time integrated correlation function is nothing else than your operator, your perturbation operator, time t equals 0 squared times the correlation time. And the correlation time, the inverse of the correlation time, is the spectral width of your Dry field, and this is what the spectral width is in Fermi's golden rule. On the other hand, if you do the integration v of t dt, think about it as Fourier transform, it gives us actually some v of omega. It gives us the Fourier transform. Well, I say it omega. If you just do v of t dt, you get the Fourier transform at 0 frequency. But if you look through the derivation we did, there was an e to the I omega resonant term, which we were just splitting out. So we have sort of shifted the origin of frequency. So therefore, the Fourier transform, if I correct for this just offsetting frequency, which I introduced for simplicity, this is nothing else than asking whether the Dry field has a Fourier component which can resonantly drive the transition. And we talked last class about the convolution. This gives actually the power spectrum. It gives the Fourier transform of it squared. But the power spectrum is, of course, when you take a field and Fourier analyze and ask what is the power spectrum, it's sort of the whole power in the whole intensity of your laser, of your field, is spread out over the bandwidth of the source. So when you say the power spectrum, a power spectrum is automatically intensity divided by spectral width, and that's where the delta function and the spectral width in the normal formulation of Fermi's golden rule come in. So I'm just emphasizing I haven't really done anything new than just giving you a general notation. And I would actually say, whenever you were asking yourself about Fermi's golden rule, this is the full truth. This is about a fully time-dependent arbitrary time field, and you realize what was v squared in Fermi's golden rule is actually just the simple case of the more general case, and the more general case is it's a correlation function or it's a power spectrum which creates the rate in Fermi's golden rule. Any questions about that? Okay, so we have this powerful formalism. So all we have to do is, when we want to understand what is the rate and the spectral width of the spectroscopic feature is, we have to understand what is the field driving the atom, and then we take the Fourier transform, or we figure out what the correlation time is. We take V of 0 squared times the correlation time, and we know what the rate is. And this will allow us major insight into spectral broadening. Okay, but after introducing that in general, I think it's time for a simple example. And as a simple example, I just thought I show you how we get the natural line widths. And of course, the natural line widths, I've mentioned several times, we need optical law equations. We have to really kind of capture the interplay between the coherent drive of the atom and the spontaneous decay. But just phenomenologically, if I say the excited state has a decay rate of gamma over 2, that's, I mentioned it before, we can capture some aspects of spontaneous decay. And that means now, remember, our spectral width comes from the correlation function of the matrix element, and now the operator is constant, but the state is decaying. So therefore, the matrix element has this exponentially decaying function. And if we then ask what is the correlation function at time 0 and time tau, we get this. And of course, the Fourier transform of an exponentially decaying function is a Lorentzian, and I've shown you now with a different formalism that yes, if you have damping in the excited state, for instance due to spontaneous decay, we get the Lorentzian. Of course, we know there should be power broadening too, but of course, don't expect power broadening from a perturbative approach, because the perturbative approach is only valid when we have weak drive fields. Questions? Okay, but now I want to, after this simple example, I want to explain to you Doppler broadening. And I hope I know I will present it in a way and draw some conclusions which are usually not done in the normal presentation of Doppler broadening. So what we have to bring in now is that we have moving atoms. That's what Doppler broadening is about. So we drive the field with an electromagnetic wave, and we have usually ignored the spatial dependence, assuming the atom was clamped down at z equals 0, but now we have to allow for motion. So the relevant matrix element for which we want to calculate the correlation function is now a spatial dependence. And our correlation function, G of BA, involves now, I call the Rabi frequency now X for simplicity, or maybe probably from whatever source I took this material, because I used it. Okay, so now we have the correlation function. We have the temporal part, t prime minus t, but then we have a spatial part, and this is now the new part, which has to account for that the atom is moving from one position to another one. And when we calculate the correlation function, we have to average now over the velocity distribution of the atom. So this new part, which will account for Doppler broadening, I call this part I, and z of t prime minus z of t is simply the velocity of the atom times the time tau. Tau is t prime minus t. So atoms move by that. And v is the z component of the velocity. So now we have to calculate that. And of course we assume that we have a Maxwell-Boltzmann distribution. We assume a Maxwell-Boltzmann distribution. And then our integral, our expression I, we have to convolute. We have this term e to the ek v tau, but now we have to convolute it with the one-dimensional Maxwell-Boltzmann distribution, where alpha is the most probable velocity. And since the velocity distribution is normalized, we have this prefactor. Alpha is the most probable speed, and mu is the mass of the, sorry, it's not mu, it's m, and m is the mass of the atom. This integral, of course, can easily be solved, and we find that provides there's a Gaussian envelope with time tau, so it's an exponential decay with time tau. And our rate, which is the matrix element, involves now the temporal integral over, let me just scroll up. In our correlation function, we had a temporal part and a spatial part, and the rate, this was Fermi's golden rule, is the time integral over the correlation function. So therefore, we have the exponential factor in time. After convolution with the Maxwell-Boltzmann distribution, we have this exponentially decaying term, and the result of that is, well, hooray, we've re-derived the Gaussian profile for a Doppler-Broad line. Okay, but yes, we want to look at this result with some new eyes, because until now you would have said, okay, that's really trivial, each atom has a velocity, Galilean transformation into the moving frame means the frequency is shifted and everything falls together, and yes, that's one way to look at it. An inhomogeneous broadening, each atom has its own velocity. But now we want to look at it from the viewpoint of a correlation function describing the whole system. So we had calculated this correlation function which the atomic ensemble experiences, and this correlation function here decays as a function of time, and it decays with a characteristic time tau c, which is 1 over k alpha, and this is nothing else than the reduced wavelength lambda bar divided by the most probable velocity. Okay, so we want to relate the line width to some form of coherence. And what we realize is the coherence time of the correlation function, which leads to Doppler broadening, is the time it takes an atom with the most probable velocity to move one wavelength. But wait, what we have is, in the Maxwell-Boltzmann distribution, the most probable velocity is also the width of the velocities. So therefore, what we can say is, if all the atoms would start at one position, after the correlation time Tc, the atoms have spread out over one wavelength. So therefore, the correlation time tells us how long is the whole ensemble driven coherently, but once the atoms, due to their motion, spread out compared to their initial position by an extra wavelength, each atom experiences now a different phase of the dry field, and that sets the limit to the coherence. And this is the point where, when we ask how many atoms are getting excited, we can no longer add amplitude in a constructive linear way. We are adding amplitudes in quadrature, and this is exactly what I explained to you at the beginning of this lecture. So let me just summarize it. Alpha is the thermal spread of velocities. And so the keyword is here, atoms in a random way spread out by lambda in the coherence time Tc. Well, the question which should come to your mind is now, but what happens when the atoms are in an atom trap and are confined and they cannot spread out? That's what we want to discuss in a few minutes. But before I do that, let me give you another interpretation which is helpful. You can regard, if you have a thermal ensemble, you can say, okay, I have a box, each atom is a plane wave with a perfect velocity, and now an ensemble of that. But very often, especially if you do localized physics, you want to regard each atom as a wave packet. And if you want to use a localized description of your gas, where atoms are wave packets, then you assume, in a consistent description, that the atoms are spread out due to the momentum spread in the Maxwell-Boltzmann distribution. This is nothing else than h bar divided by the mass and the most probable velocity. And this is foregoing factors on the order of unity, nothing else than the thermal de Broglie wavelengths. Okay, so now we have the picture that the atom is a wave packet in the ground state, but now we excite it with a laser. Well, if we excite it with a laser, some atoms go, part of the wave packet goes to the excited state, but the atoms in the excited state, because they have absorbed the photon recoil of the photon, are now moving away from the ground state part of the wave packet with the recoil velocity with this h bar k over m. So if I regard the atom as a wave packet, the natural question is, when does the ground state part of the wave packet lose overlap with the excited state part of the wave packet? Lose overlap after time. Well, I derive it for you, but it can only be the coherence time. So the time is, it is the size of the wave packet divided by the velocity of the recoil velocity. The mass cancels out, h bar cancels out, and this is 1 over k alpha, and this was exactly our coherence time. So therefore, when I'm telling you, you should understand in this picture Doppler broadening as a loss of coherence for the ensemble, you have now two ways to describe it. One is you can say in a more quantum mechanical way, after the coherence time, the recoil velocity has separated the ground and excited part of your wave packet. Or you can say when the atoms in the ensemble have a velocity spread of alpha, then they have spread out by the optical wavelengths. So these are two equivalent pictures to understand why this ensemble is no longer coherently driven.
One thing that confuses me is in both the pictures, like why is in the first picture the optical wavelength not relevant, and the second one the deep wire wavelength not relevant for coherence distance?
Well, because these are two different pictures, but the results agree. I mean, the wavelengths comes into the picture with the wave packets through the recoil velocity, because the recoil velocity is h bar k over m, and k is the inverse wavelengths.
Right, but like when we write delta t there, we write the wavelength of the packet here, and we could have also just thought of it as when does the atomic ensemble become bigger than the optical wavelength. But here we are talking about the deep wire wavelength.
I think for consistency, I give you a quick answer. I should think about it longer. But what we usually assume when we describe atoms by wave packets, we assume the atoms are not cooled below the so-called recoiling. So we assume that the thermal de Broglie wavelengths is shorter than the optical wavelengths. And so then you would, if you would say, you would expect also that there would be something happening when the wave packet spreads out by an optical wavelength. I want to think about it more, but the quick answer is just assume what is usually the semi-classical limit of these kind of pictures, where we assume that we have a hierarchy, that the thermal de Broglie wavelengths is much larger than the size of the atoms, but smaller than the optical wavelengths. A few things happen really in intuitive pictures when you cool atoms below the recoil limit. Okay, there's one reason why I would like to express that to you. Armed with that knowledge, if I would now ask you, you have a trapped Bose-Einstein condensate, and you take the spectrum. What is the Doppler width of the spectrum of a Bose-Einstein condensate? It's in the Maxwell-Boltzmann distribution. No, the condensate is different. It's in one quantum state. But now you can choose your picture. One picture you can take is, you can say the de Broglie wavelengths here has to be, the wave packet loses overlap when the excited state moves one de Broglie wavelengths. But the condensate is fully coherent. So you would now say, maybe I should think about it if the condensate, part of it is coupled to the excited state, and with a recoil, the excited state component has moved the size of the condensate. Replace the de Broglie wavelengths by the size of the condensate. And this is the correct answer. You would then find out what is, quotation mark, the Doppler broadening of a condensate. Of course, you could have also said the condensate has a certain size. H bar divided by the size is the momentum spread due to Heisenberg's uncertainty relation. And now I plug in this momentum spread into a formula for the Doppler broadening. And you would get the same result. But especially when you think in terms of a coherent wave function, this picture of losing overlap between the two parts of the wave packets is very intuitive, very useful, and it actually guided a lot of our intuition when we looked at the limitations of superradiance and optical spectroscopy with Bose-Einstein condensates. Any questions? Okay, so now we are ready to take it to the next level. When I told you that the spectral width is the inverse of the coherence time, and one way to think about the coherence time is that the particles spread out over one wavelength. So if you take this thought seriously and say, what happens if I confine atoms in a container or an atom trap to less than the optical wavelengths, then you would say they can never spread out by an optical wavelengths. Does that mean that the coherence time is now infinite and that we can do spectroscopy which is no longer affected in any way by Doppler broadening? Well, what I just motivated in words is the so-called Lang-Dickey limit of tight confinement. And as I want to show you now, yes, indeed, you have a very, very sharp line which is not broadened by Doppler broadening, which is not shifted by the recoil shift. It's really the unperturbed line of the atom which can be probed by confining the atoms to less than a wavelength. So therefore, let's now discuss the line shape of confined particles. So what I want to present you now is we have particles trapped in a harmonic oscillator, and in one limit, which I want to explain you, we should just find the normal Gaussian Doppler profile which we have obtained for free gas. This must be the limit when the harmonic confinement is very, very weak. But for tight confinement, we should actually find, unless we assume other means of line broadening, a delta function spectral feature. And I will explain to you that this is actually the same as the Mössbauer effect. It's a Mössbauer line due to the confinement. So therefore, to have trapped particles allows us to go to the ultimate limit in precision spectroscopy. What happens when you have trapped particles? The Mössbauer effect, which I mentioned, was simply the effect of confinement. In other words, the trapping potential is completely eliminating the Doppler effect, but I want to be specific. It only eliminates the first order Doppler effect. Everything I just did with the correlation function assumed first order Doppler effect. If you want to get rid of the second order Doppler effect, then you need some form of cooling. But usually when you do experiments with trapped particles, you do confinement and cooling at the same time. Okay, let me start out with very basic things. So let's talk about the spectrum of an oscillating emitter. If we have an atom, it undergoes a transition from excited state B to excited state A. This is an internal state, but now we want to include motion, and we have to include the external degree of freedom. And for our discussion right now is the external degree of freedom is an harmonic trapping potential. So now we look at the combined system, you can say Hilbert space, which combines external and internal motion. And of course, the external motion is now quantized, I can assume, but it doesn't really add anything to it at this point, that the trap frequency in the ground and excited state are different. I simply assume that the trap frequency, omega trap, is the same. This, of course, is excellently fulfilled in ion traps. If you would do spectroscopy of neutral atoms in a dipole trap, of course, the ground and excited state may experience a different AC Stark shift, and then you have to account for two different frequencies. But let me just make this simplifying assumption. So if you assume that an atom emits radiation, it will, for energy conservation, emit at the electronic energy, but then there is an extra term which in general is the energy of the external motion, or the trapping potential for the initial state minus the final state. And if we now make our simplifying assumption that everything is harmonic, the trapping potential is harmonic, and the trapping frequency is the same in the excited state and the ground state, we simply have the electronic energy plus n quanta. N is the change of the number of quanta of the harmonic motion. I want to point out, it looks so trivial, but you should at least think for a second about this statement, that this formula includes the Doppler shift and the recoil shift. And of course this is trivial, because we are talking here about the total energy of the external state, the total energy of the final state after photon emission, and the energy in the trapping potential includes all the kinetic energy of the particle, which includes whatever comes from recoil velocity or from the motion of the atom. So therefore, we obtain what is called the sideband spectrum. I just show you a stick diagram. Here is the electronic transition, and then we have sidebands, and the spacing of those sidebands is nothing else than the harmonic oscillator frequency. Any questions? At that level, I want you to appreciate that this is radically different from Doppler broadening. There is no Doppler broadening. By fully quantizing the motion in harmonic oscillator, we obtain a discrete spectrum. And what I want to show you is, when we calculate the intensity in the peak for strong confinement, almost all of the intensity is in the central peak, and therefore there is no Doppler broadening. But I want to later show you how we can go from the discrete spectrum back to the Doppler broadening, which we just described in free space. So you should say, well, but the motion, the recoil, it must come in. Where is it? Well, it's not in the stick diagram. But the sticks are the only possibilities for the possible photon frequencies or photon energies. But the question is, what is the amplitude? What is the probability that this will happen? And you already see where I'm aiming to. In the limit that we have many, many sticks and we are not resolving the sticks, we will get back to the standard Doppler broadening. But so the big question is, how many of those sticks do we have? Are we in the limit where things are heavily discrete? This is our new limit, or do we have many, many of them? So therefore, the recoil and the velocity, they really enter when we calculate the intensity. And whatever our formulation is with Fermi's golden rule, the rate is proportional to the relevant matrix element squared. And now I want to show you how we calculate those matrix elements. Any question?
But is it true that each of these sticks has the line width of the intrinsic line width of the atom?
Yes, we come to that in a few minutes. I ignore here the spontaneous broadening just for pedagogical reasons, but a little bit later I first want to sort of discuss the number of sticks. Do we have a few? This is sort of new, then we have only a few sidebands and we have the Mössbauer effect. If we have many, that's sort of more the continuum which we describe with the classical velocity distribution. That's my message number one. But then the next message is, do we resolve the sticks? Do we have resolved sidebands or not? And for that, the criterion is the natural line width larger or smaller than the sideband spacing? But they're sort of actually, it's not just one parameter, there are two parameters. One is, which will be the Lambdicke parameter, how many sticks do we have? And the second question is, do we resolve the sticks? And you can say there are 4 different regimes, yes or no for question 1 or yes or no for question 2. Other questions? Okay, so the rate is proportional to the matrix element squared. And yes, we have all kind of the matrix elements involving the internal degree, but the new thing is the matrix element for the center of mass wave function of the atom, which is, you can say, just the Hermitian, the polynomials for the harmonic oscillator. So we have the eigenfunctions for the harmonic oscillator between initial and final state, and what acts on the only part of the electromagnetic field operator which acts on the position of the atom is this term e to the minus ikr. Okay, I mentioned already that the new regime is that the confinement is tight. So let's just look at this situation when kr is much smaller than 1. Then we can expand this exponential into 1 minus ikr. And now I want to remind you that the position operator, when we treat the harmonic oscillator, is nothing else than a plus a dagger. So therefore, if kr is small, and therefore we can do the first order expansion of e to the ikr, our spectrum, our operator is here 1 minus prefactor a plus a dagger, and therefore the only possible sidebands are the one where the change in harmonic oscillator quantum number is plus or minus 1. So we are already obtaining the result which is called the deep Lambdicke limit when kr is much smaller than 1, that we have a strong carrier. We have only 2 sticks, the delta n equals plus minus 1, and the intensity in each of those sticks is actually proportional to k square r square, which is nothing else than the square of the extension of the atomic wave function, and k is 1 over lambda bar square divided by the optical wavelength squared. So we see already, without any major formalism or mathematical tools, what happens in the limit of tight confinement. The spectrum of confined particles is neglecting the spontaneous line widths. The delta function, without any Doppler shift, without any recoil shift, right at the resonance frequency, electronic frequency of the atom. And what is the only thing which is reminiscent of the motional degree of freedom are those small satellites, but their intensity goes to 0 with the extension squared over lambda squared. So therefore, if we confine a particle to less than an optical wavelength, in the older picture I told you, it can never spread out over wavelengths, can never get out of coherence with a dry field. And here we have a quantitative description that at that moment we can obtain spectroscopic information about the resonance, completely unperturbed by motion effects. Questions? Okay, so that was maybe the most fun part, the extreme limit, and you realize what happens. But now we want to sort of fill in the gaps. I first want to sort of contrast what I just described to you with the semi-classical picture. In the semi-classical picture, if you have an emitting oscillator or absorber, we have an electromagnetic plane wave, we can now ask, what is the phase? What is the phase of the plane wave experienced by the atom? And of course, the phase is affected by the motion of the atom. If we assume the atom moves in a track with harmonic frequency omega t and an amplitude x naught, then this here is the phase seen by the atom in its own reference frame. And if I then define with double quotation mark, because it's sort of something which needs explanation, if I define an instantaneous frequency, which is nothing else than the derivative of the phase, then I retrieve the Doppler broadening, the normal Doppler broadening. So now you see where sort of normal Doppler broadening would come in, but the question is, you cannot measure an instantaneous frequency that would, violate the Fourier theorem. But if we can apply, if sort of the atom oscillates slowly enough, the motion is slow enough that we can apply the concept that we can look at the frequency the atom experiences. You would at least say, before the atom changes its velocity, it should see a few cycles. If it oscillates very fast, this concept, of course, cannot be applied, but at least you see where your normal Doppler shift comes in. It comes in the concept of an instantaneous frequency. Of course, what we should do now is, we should not take the concept of the instantaneous frequency, we should rather do it correctly. What we have is, we see we have the phase of the atom, so therefore we should, by using the motion of the atom for x, we should perform Fourier transform. The Fourier transform tells us what is the true spectrum which the atom experiences. So therefore we take this plane wave, we put in the oscillatory behavior of the atom, and then we take a Fourier transform. Okay, so the electromagnetic field seen by the atom has an amplitude, which is the cosine of the phase, and the phase has the temporal dependence, that's just the frequency of the plane wave. But now the position involves the oscillation of the atom at the track frequency omega t. And what I've introduced here is the delta factor is called the modulation index. This is the relevant quantity. It is k, which comes from the plane wave, e to the ikr, times the amplitude of the atom. And so the modulation index is nothing else than the amplitude of the atomic motion divided by the wavelength or the reduced wavelength of the light. Just if you remember for a second, this extreme stick diagram where we had one big stick and two smaller sticks, remember the intensity in the smaller sticks was the extension of the atom divided by the wavelength squared. So we had exactly the same parameter, but the previous description assumed a quantized picture for the harmonic oscillator. I really used A and A daggers and the atomic wave function. This is a semi-classical picture where I treat the oscillation of the atom in a classical description. But in both cases, of course, the relevant parameter is the ratio over which the atom moves, the amplitude of the atomic motion or the size of the atomic wave function in relation to the wavelengths of the light. Okay, so we want to Fourier transform this function, and this gives us the spectrum. I can show you the result is that we can have a Fourier expansion of this amplitude, and it involves Bessel functions. So it is a Bessel function Jm, which tells us what the intensity is in the nth sideband. And the argument of the Bessel function, whether we take the Bessel function at the origin or at a finite argument, is given by beta, the modulation index. You can immediately, in just 2 lines, derive the Fourier transform. All you have to use is those identities which involve the beta function, which involve the Bessel function. Whenever you have the cosine of a sine or the sine of a sine, and you do Fourier transform, you get naturally Bessel functions. Okay, so let's just look at the result. We talked about the stick diagram. The stick diagram was actually motivated quantum mechanically, but now we also find a stick diagram purely classically because of the periodic motion in the harmonic trap. But now what we obtain in the semi-classical limit, we obtain what is the height of each stick. Well, the height of the stick, which is n sidebands away, is given by the square of the nth Bessel function, and beta is the modulation index. And if beta goes to 0, that means the atom is not moving at all, the amplitude x0 is 0, this is the limit of tight confinement, then all Bessel functions are 0 except the zeroth order, and that means we are back to a single delta function, a single stick in our stick diagram. So let's now take the result and discuss it. So how does the spectrum look like? Well, I want to give you 2 limits. I want to give you 2 limits where the atom is extended much larger than the wavelengths. This means large modulation index beta and small modulation index beta. So, but first, what in the limit where beta is large, for large beta, the argument of the Bessel function becomes just cosine beta minus phase. So if we use that, if we assume a thermal distribution where beta over kT d beta squared. So we take our spectrum and we just convolute it with a thermal distribution of amplitudes x naught, which is of course just the Boltzmann factor. And in that limit, we actually obtain a spectrum where the envelope of the sticks looks like the Doppler bits. So if those two conditions are fulfilled, then we obtain the normal Doppler bits. If in addition we assume that the sidebands are not resolved because the natural line which is larger than the spacing, so if we assume that in addition, then we just find the normal Doppler broadening the way how we have derived it. As in free space. So normal Doppler broadening is the limit of a large modulation index, a thermal distribution of modulation index, and the case of not resolved sidebands. The opposite limit, of course, is when beta is much smaller than 1. That means the amplitude of the oscillating particle is smaller than the wavelengths. I mentioned it a few times, so I should write it down. This is the Lamb-Dickey regime. And then the relevant approximation for the Bessel function is in the limit. And this limit is 1 over n factorial times beta over 2n. And for the case that n is 1, this is just beta, and the amplitude squared is beta squared. It's x naught over lambda squared, as we had discussed before in the quantum mechanical limit. So you'll see that to use matrix element for the harmonic oscillator or use a semi-classical Fourier transform with the Bessel function, both lead to the same result, that deep in the Lamb-Dickey limit we have essentially 3 peaks. And the satellites are quadratically small in the modulation index squared. So this regime is particularly interesting for atomic clocks and for metrological applications if the sidebands are resolved. If the sidebands are not resolved, you have sort of a line shape which depends, let's say, on temperature, because x naught squared, which is the thermal excitation, is proportional to temperature. So as you cool it down, you will actually see that your line shape changes. But the good thing is that once you resolve the sidebands, the line shape of the central carrier does not change anymore. And once you can resolve the sidebands, you can just observe the central carrier, and you obtain spectroscopic information which is no longer blurred, which is no longer affected by motion and by temperature. And that's, of course, the regime where the atomic frequency standards want to operate. Questions? Okay. Yes. Let me just write it down because it's important. For resolved sidebands, you have sharp lines, no motional broadening, And the physics I described to you is actually analogous to the Mössbauer effect. In the Mössbauer effect, the intensity of the recoilless emission of this recoilless line is described by the Debye-Waller factor. So in this case, the Debye-Waller factor is 1 minus the probability for the two sidebands. So the same concept of Mössbauer line and Debye-Waller factor describes the physics for tightly confined particles. So if I use the analogy to the Mössbauer effect, the Mössbauer effect is called the recoilless emission and absorption of X-rays. So what we have here is we have a recoilless absorption and emission of photons. Of course, the photon which is emitted and absorbed has momentum. There should be momentum recoil. So the question is, where does the momentum recoil go when the confined particle emits or absorbs on the carrier on the central line? How do we reconcile the result I derived for you with momentum conservation? Trapped particle, tightly confined, and photon comes, has momentum, the atom absorbs it. But the spectrum does not show any evidence for recoil shifts and such. Colin?
Must be absorbed by the trap somehow.
Must be absorbed by the trap, yes. Your trap is anchored in the laboratory, and you transfer the momentum. The atom is attached to the trap is attached to the laboratory. So the object which takes over the momentum is your whole apparatus, or in the extreme case, the whole building. And there is, of course, a kinetic energy associated, momentum squared over 2m, but the mass is now the mass of the building. So therefore, there is no energy associated with absorbing the recoil. So it is as if, and this comes back to some earlier remarks I've made is that when you have this absorption in the Lendicki regime, it is as if your two-level system has an infinite mass behind it. And that's sort of the situation how I told you should often think about it. You should separate effects of the internal degree of freedom and the external degree of freedom by just assuming, I can assume first that the atom has infinite mass, and once the atom has infinite mass, the motion degree of freedom doesn't matter. And what I just explained to you is a practical way to endow your particle with infinite mass. Just connect it with tight confinement to your apparatus. And then for the momentum exchange with a photon field, it is actually the mass of the whole apparatus which matters. Questions?
Is there a more direct way to think about this for maybe the example of a magnetic trap, the mechanism by which this momentum is transferred or absorbed?
Okay, magnetic traps for neutral particles are usually not in the Lendicki regime, so you have to be a little bit careful. And but the explanation would be the same. The magnetic fields are like tight springs which connect the neutral atom to your coils. So, and therefore, you should just think about the magnetic trap in a mechanical model. Your neutral atom is connected to your coils with springs, and if you now hit the atom with a photon, because of the quantization of the discreteness of the spectrum, the photon in most cases does not have enough recoil to create a mechanical oscillation of your particle. The momentum goes through the springs to the support structure. But occasionally, with a probability which is a modulation index squared, you will actually promote the particle to the first state of harmonic motion. And then the atom has acquired some kinetic energy. But this probability can be made as small as you want by going to a smaller and smaller modulation index. That's the way how I would think about it. Nancy.
About the multiple lines that we get, I was wondering if the levels of the harmonic trap itself are blurred, which could happen in the lab if the traps are like, if the trap depth is moving, for example, the levels of the trap could get blurred. Would that result in additional broadening of this, or how would that affect?
It depends. I think if you have some temporal broadening and so you just plug it into your correlation function, whatever shakes your system, if that means the atom sees some shaking in the phase of the electromagnetic field, it affects it. If you have an ensemble of atoms, or if you do the experiment repeatedly and your repeated measurements are the ensemble, and every time you do the measurement, your magnetic trap has a slightly different current and therefore slightly different confinement, well, what you would see is that those side bands fluctuate, but the carrier is independent of the trap frequency. So therefore the carrier is actually, the central peak would not be broadened by fluctuations in the harmonic confinement. Let me just make one comment. I derived the result for you, at least that one, by taking the amplitude of the atomic motion, the amplitude of the phase, and doing the Fourier analysis. I mean, this is exactly what we learned from the mechanism or from the formalism of correlation function. We should take the amplitude of the perturbing field and Fourier analyze it. I didn't phrase it here in the language of correlation functions, but what I did was exactly what we learned from the correlation function formalism. Okay, let me maybe summarize in words what we learned. So what we learned from this discussion is that what matters for line broadening and obtaining spectroscopic information is the accumulated phase, the phase which the atom accumulates. And if different atoms in the ensemble accumulate a phase which is different by 2 pi, at that moment we have reached what we call the coherence time, the coherence time of the correlation function, and the inverse of this time is a line broadening. But now we also discussed the case of tight confinement. The atom can be in very, very rapid motion. And the phi dot, the change of phase, can be very rapid due to the instantaneous velocity. But if the atom turns around because it's an oscillatory motion, positive and negative Doppler shifts completely cancel. Because you never allow the atom in this periodic motion to acquire a net phase. And therefore the motional broadening is absent. But so one way to think about this carrier is that the atom rapidly oscillates through plus kV and minus kV Doppler shifts, and the two cancel. So this is the reason for that. Okay, I think we are now very well prepared for Dicke narrowing. Actually, I have to say it's the first class this semester that I was teaching a little bit faster than I assumed. So I'm now right at the end what I prepared for today, but I know my notes sufficiently well that I can go on for 10 minutes. But so the Dicke narrowing, the last time I looked at it was 2 years ago. But let's get the physical picture. So I want to now apply what we have learned, not to a trapped atom, but to an atom which is embedded in buffer gas. So just think one rubidium or one sodium or one lithium atom, and it is surrounded by a buffer gas of argon or neon. And I know sometimes when we do saturation spectroscopy to stabilize our lasers, we have a little glass cell which has sodium or rubidium in it, but we also put an argon buffer gas into it. So that's the situation I want to describe now. But Colin, you had a question.
Yeah, you wrote down the condition for resolving the side bands as your natural line width being or your trap frequency being larger than your natural line width. In alkalis, if you had like, say, we're 10 megahertz line width, how do you actually like resolve this without a ridiculously? People do sideband cooling like in a lattice. They don't have 10 megahertz trap frequencies.
Okay, so good question. The question is the resolved sideband limit. How can we reach it? Well, it can be reached in ion traps. In ion traps, because you can put kilovolts on electrodes, you can really create harmonic oscillator frequencies which are many, many megahertz, and then you have the resolved sideband limit, assuming that the natural lifetime, but that's the case of many ions, is in the megahertz region. For neutral atoms, it looks like, mission impossible. However, there is a way out, and this is the following. One is you can maybe have a one-dimensional optical lattice. So in the lattices, you at least have tight confinement of many, many kilohertz. But now you want to use a very narrow transition. If you use a very, very narrow transition, then even for 10 kilohertz external harmonic oscillator potential, you are in the resolved sideband limit. Now, for alkalis, you won't find an excited state which has a natural line width of 10 kilohertz. But, and this will be our discussion on Wednesday, that if we use a Raman transition, we go from one ground state with an off-resonant laser to another ground state. Topic will be two photon transitions, but those two photons, since there's no intermediate state, can be regarded as click-click. You absorb two photons, and in some picture, that's a message I will give you next week, they are equivalent to a single photon. So now you have a two photon but transition which transfers recoil to the atom. So the effective wavelength of the two photon transition is, because you have twice the photon energy, you have two photons involved which both have a recoil, so the effective K vector is 2 times the K vector of an atom. But the spontaneous line width is close to 0, or is literally 0, because you have a Raman transition between two ground states. So Raman, if you do Raman sideband cooling of neutral atoms, then you reach the Lamb-Leakey limit, you reach the limit of strong confinement. But you need a very narrow transition, and there are, of course, some atoms which have a very narrow clock transition, but for many, many atoms which have hyperfine structure, you can resolve to a Raman transition. Okay, let's now talk about Leakey narrowing. So we have a situation that we have an atom in buffer gas, and in most situations when you put an atom into buffer gas, you get what is called collisional broadening. I will talk about collisional broadening on Friday. Just a reminder, we have class on Friday and not on the following Monday. So on Friday we'll talk about collisional broadening, and I will discuss, for instance, the model, an atom in the excited state. When it collides, it gets de-excited, and then you have pretty much the situation where you have, in effect, a shortened lifetime of the excited state, and what you get is a Lorentzian which is broader, which has a width not of the natural line width, but a width which is the collision rate. But there are situations, and that's what I want to discuss here, that we have atoms in a more benign buffer gas and where we can assume, and this is actually fulfilled, that collisions do not change well, they're not de-exciting the excited state, but they're not even changing the coherence between ground and excited state. So the phase evolution, the internal state, ground and excited state, just, you can assume you have a Bloch vector which oscillates, and the Bloch vector superposition of ground and excited state oscillates at the natural frequency, and this Bloch vector just rotates. It doesn't have a hiccup, it doesn't change its phase when the atom collides with a buffer gas atom. So we assume that we have such a buffer gas where collisions don't change the internal coherence. And by internal coherence, I mean the phase between the ground state and the excited state. So in this situation, but it's actually a very important situation which has been reached in many cases, in this situation we have, thus the buffer gas acts only on the external motion of the atom. And now you can say in some way the buffer gas acts like a trap. The particle wants to fly away, but it collides with the buffer gas atom, and with a certain probability or after a few collisions it returns back to the origin. However, it's a lousy trap because there is some randomness and diffusive motion. So if you want to describe it as a trap, it would be a trap with a wide spread of trap frequencies. Okay, so if we use this picture now, what we have learned from ion traps, remember we had an ion trap with a sharp carrier, and then we had side bands at the trap frequency. But if we have sort of now a lousy trap, which in each realization or each moment has a different trap frequency, and I'm waving all my arms, I would say for the other part of the ensemble, we get a carrier and we have something else. And for another realization, we have another trap frequency. So if I use a little bit of artistic intuition here, I would expect, based on what we learned from the previous discussion, that in such a buffer gas, I would have a sharp carrier, and then I would have sort of a pedestal, which is the envelope of many trap frequencies. And we know sort of that the envelope of all our sticks, this was actually given by the Doppler effect. So what we may expect now is that in this situation with buffer gas, we get a sharp line, and then we have this broad pedestal, which you can think, at least in some intuitive picture, as smeared out side bands, and I may call that the Doppler pedestal. And we would expect, and I discussed that with the Bessel function, that there is one limit where the envelope of all those sticks eventually looks like a Doppler broadened line. Anyway, time is over, but let me just give an outlook. On Friday, what I want to do is I want to calculate the width of this line with you. And remember, all we have to do is we have to calculate the correlation function. Previously, when I derived for you Doppler broadening, the correlation function was the kx became kvt. Where x became vt, how much the atom moves with the velocity v. By simply replacing the linear motion v times t with a diffusive model, we can calculate the line shape, and we will actually find that the central line is not infinitely sharp, but it has a width which is given by the diffusion constant. And if the diffusion constant is very, very small, we approach a very sharp line. And the final comment is, and this is called Dicke narrowing. It is this counterintuitive result that collisions, if they have those properties, are not broadening the line. They actually narrow the line from the usual Doppler width to something which is much sharper, and this has been useful for high precision spectroscopy. But I think with the concept which we discussed today of confinement, you realize why collisions can actually reduce the line width, namely by preventing the atoms from acquiring phases, random phases with respect to the dry field quickly. Any questions? So see you on Friday in this other building, this other lecture hall which has been announced on the website.
It's every night.